Welcome to this presentation. My name is Peng. I'm an assistant professor in Singapore University of Technology and Design. Together with Yingjie Cheng, who is a PhD student in University of Science and Technology of China, as well as a visiting student in Singapore University of Technology and Design. We will present our research work on spatial-temporal motion control via composite cam-follower mechanisms. In this research, we focus on path generation mechanisms, which are mechanisms that can move a point along a prescribed path. Here we show an example, which is a 4-bar linkage. When the left bar is driven by a single motor, the endpoint of the right bar will generate a path. See the arc in purple. Compared with robotic arms, path generation mechanisms typically require a single driven motor to generate a path. This brings several advantages like low cost, easy to control, and energy effective. Due to these advantages, path generation mechanisms are used in a wide variety of applications, including drawing machine that can draw a target curve, mechanical automata that can display interesting motions to entertain people, and a walking robot whose leg moves following a specific path to walk. Currently, there are two kinds of mechanisms for path generation. The first kind of mechanisms are based on linkages. Linkages are lightweight and easy to fabricate, making them widely used for path generation. However, linkages can only approximate a given path instead of exactly realizing the path, since they only have a limited number of design parameters. The second kind of mechanisms are based on plate or 3D cams. Plate or 3D cams can achieve precise motion control, not just on the trajectory, but also on the timing. However, their limitation is that they can only generate very simple motion paths. In this work, our goal is to design mechanisms for exact path generation. The user can specify a target path represented as a free-form closed 3D curve. The user can also specify a timing requirement on the motion represented as a set of key points on the target path, as well as the timing intervals between each pair of key points on the time slider. Taking the user specified path and the timing as input, our goal is to design a mechanism whose output motion can exactly follow the path and timing. As shown in this example. We choose cam-follower mechanisms, abbreviated as CamMech, as building blocks to achieve our goal of exact path generation. Look at this convention CamMech. The big cyan part is a 3D cam. The follower is in orange, and the support structure is in gray. As aforementioned, conventional CamMech can only output simple motion paths, such as linear paths shown here. The reason of this simple motion path is that the 3D cam can only push the follower along a specific direction, since the cam-follower joint is modeled as a cylinder move-in groove joint. Inspired by this observation, we modify the cam-follower joint such that our CamMech can generate a much more complex free-form curve. Thanks to our ball move-in groove joint, our cam can push the follower along a variety of directions to transfer complex motion. In our CamMech, the follower support joint determines the type of the follower's output motion. In this example, the follower support joint is a modified ball joint. Hence, the follower can output 2 degrees of freedom rotational motion. By changing the follower support joint, we propose 6 classes of CamMechs that can output different types of motions. The first class can output 2 degrees of freedom translation by using a sliding joint. The generated path can be any freeform curve on a planar surface. The second class can output 1 degree of freedom oscillation and plus 1 degree of freedom rotation by using a cylindrical joint. The generated path can be any freeform curve on a cylindrical surface. The third class can output 2 degrees of freedom rotation by using a modified ball joint. The generated path can be any freeform curve on a spherical surface. Our CamMechs also support outputting 1 degree of freedom motion, including 1 degree of freedom translation, 1 degree of freedom oscillation, and a 1 degree of freedom rotation. The output path can be a straight line, a straight arc, or a straight circle, respectively. Our problem in this work is to solve the exact path generation problem by using our proposed CamFollow mechanisms. In other words, we want to design CamFollow mechanisms whose output motion can exactly follow user-specified path and timing, as shown in this example. To address this problem, there are 3 challenges. The first challenge is to model each CamFollow mechanism, including parameterizing its geometry, computing its kinematic equation, and dynamic equation. The purpose of this modeling is to understand how our CamMech works, as well as its kinematic and dynamic behavior. The second challenge is to compose multiple CamMechs. This is because one CamMech can only generate a single path. To generate multiple paths, we need to compose a set of CamMechs to form a working mechanism, also called composite CamMech. In this example, the composite CamMech can generate 3 paths, taking our 6 classes of CamMechs as the building blocks. The last challenge is to design a composite CamMech to exactly realize user-specified paths and timings. For example, user-specified 6 paths as well as the corresponding timings on the left. And our task is to design a composite CamMech whose end effectors can realize the 6 paths while driven by a single motor. Our design space is huge, including the composite mechanisms, topology, layout, and geometry. How to explore the design space efficiently is a challenging problem. With this, I would like to hand over to Yingjie Cheng, who will present our approach to address these 3 challenges.
Thanks, Song. Our work has 3 key contributions to overcome these challenges. Firstly, we parameterized the geometry of these CamMechs, formulated analytical equations to model their kinematics and dynamics. Secondly, we presented a method to combine multiple CamMechs into a working mechanism. Thirdly, we propose an approach to designing composite CamMech to realize user-specified spatial-temporal motions. Our first contribution is CamMech modeling, including how to model the geometry, how to compute the motion of CamMech, and how to calculate the torque required to drive the cam. For geometry modeling, we need to model following 6 parts: cam, follower, support, cam follower joint, follower support joint, and cam support joint. Next, I will talk about the cam follower joint. This joint is a ball moving groove joint. The groove is a swept surface from the moving follower ball, and it's always tangential to it. The center line of the groove is called the pitch curve. We can model the groove as a tube around the pitch curve. After that, the 3D cam geometry is modeled as a watertight surface that holds the groove surface. And the center of the follower ball is always on the pitch curve. Then I will talk about the CamMechs modeling. Our goal is to compute the follower's motion, given the CamMech geometry and cam's motion. The key is to find the motion transfer function. From cam's motion, a rotation driven by the motor, to follower's motion. The first constraint is that follower ball center is always on the pitch curve, where PP is follower ball center, CS is pitch curve, and TC is the cam's rotation. And the second constraint is about follower's geometry, which has different formulations for different types of follower support joint. Take this Cam2R as an example. It can output motion on a spherical surface, where PP is follower ball center, and PS is follower support joint center. The distance between 2 points is constant, since the follower is a rigid body. We got the formulation like this. With these two constraints, we can compute the position of follower ball center, and then get the motion of followers. Here is the result. For dynamic modeling, our goal is to compute the required torque for driving cam, given followers workload. While the geometry is fixed, the torque is related to 4 factors: cam's angular acceleration, follower's acceleration, follower's angular acceleration, and workload. The first 3 of which can be calculated in kinematics. Assumption: the friction is ignored, since our dynamic modeling is to efficiently quantify different designs for geometry optimization, rather than precise physical simulation. We use a 2-step approach to solve the dynamics. First, considering follower, then cam, and the curve formula is Newton's second law, which gives us the final result. This polar plot shows the torque required in 1 revolution. Our second contribution is to create a working composite CamMech by combining multiple CamMechs. We have 2 ways to connect a pair of CamMech. Type 1 is called multiple connection, which support multiple output motions. In this example, connected CamMechs can output a dog and a line. We use the sign circle for the cam and the yellow circle for the followers. The arrows are the motion transfer function. So in multiple connections, 1 parent node connects with 2 children nodes. Another way to connect a pair of CamMechs is called Cheng connection, which can adjust pose of output motion relative to the input motion. In Cheng connection, the first CamMech must output a rotation, since its output next CamMech's input. With these 2 connections, we can compose multiple CamMechs following a tree structure. In this tree, the root node is a motor. The middle node is CamMech 1R, which can output a rotation, and each leaf node is an effector. Here is the result of composite CamMech. We can use dual tree to modify kinematics and dynamics of the composed CamMech. Our third contribution is to design the CamMech. Firstly, we give an approach to design a single CamMech. Then we design and optimize the composite CamMech. For single CamMech designing, the input is a smooth, closed target curve with timing constraints. The output is 1 CamMech that can exactly realize the given motion. The objective function is composed with 2 parts, torque and weight. We want to drive the cam with a small motor, so we need to minimize the required torque. At the same time, we want to reduce the manufacturing cost, so we include the weight of the cam in objective function. It has several constraints. First, the end effector must realize trajectory. Second, timing constraints. Third, the cam groove should be smooth. Fourth, suitable follower support joint for different motion type. Fifth, cam must push follower all the time. The cam's velocity should be larger than followers at the cam follower joint. The search space are the distance from follower support joint to cam's rotation axis, the angle theta, and the pitch curve CS. We use a gradient-based method, MMA, to solve this optimization. Here is the result. For composite CamMech design, input are several target curves and timing control for each curve. Output is a composite CamMech that can realize given motion. The objective function is composed with 3 parts: required torque, the hull weight, and the dimension. Besides the 5 constraints for a single CamMech, we need to avoid connection among composite CamMech. The search space includes parameters for each CamMech and layout parameters among connected CamMech. To design composite CamMech, we need to determine the topology first, and then alternating optimize the layout and each cam geometry. Please refer to our paper for more details. Here is optimized result. The scorpion swings its princess to attack. Now, let me show some evaluation. We use CamMech 2R to draw a leaf. It can achieve complex curves. However, the more detail the leaf has, the bigger the cam is. To evaluate time control, we draw the same star with different time constraints. All of them can achieve the trajectory and reach given points at a specified time. Last, they can reach the end at the same time. It's an evaluation about Kinematic. We use CamMech 2R to draw a T-Rex curve on a spherical surface. And we fabricate it with assembly-based FDM 3D printing. We use image-based object tracking to show the drawing curve. Last, we project a target curve to the image. The difference between 2 curves could be caused by fabricating assembly or object tracking. We use Cam1T to evaluate dynamics. Optimized cam can output large force, so for the same workload, it requires less input torque. More results. We design a 6-leg walking robot, driven by a single motor. It can achieve given gaits to realize user-specified trajectory temporal motion. We 3D printed it, and the robot can walk stable and smoothly on the ground. Here are more results: drawing car, cats, flower. We can use the composite CamMech to create some mechanical toys, which has complex curves and timing control. Here is the mechanical toys about boxing, which is achieved by 3 cams. In conclusion, we present composite cam follower mechanisms for exact spatial-temporal motion control. We model geometry, kinematics, and dynamics of CamMech. We compose multiple CamMechs to form a working mechanism. And we design and optimize a composite CamMech to realize user-specified motions. Future work. Firstly, we could consider friction in dynamic modeling. Secondly, we want to combine CamMech with linkages and gears to extend capability. Last but not least, we would like to explore potential application in robotics. Finally, thank you for your listening.